Yes, I'm ready.
Requesting all to take your seats. We'll begin the session shortly. A very good afternoon to all of you gathered here. This is your host, Sonia Menezes, and I welcome you all on this very beautiful afternoon. Today, we're going to have the first session on importance of CVD and HPHT to make India #1 hub in producing industry-grade diamonds. It is an absolute honor to introduce Dr. M.S. Ramachandra Rao. Dr. Rao is a senior professor at IIT Madras and a fellow of the Institute of Physics, UK, an alumnus of IIT Kharagpur with MSc and PhD degrees. He has served as a postdoctoral research scientist at CNRS France and TIFR Bombay. He has also held prestigious fellowships, including the Alexander von Humboldt Fellowship, Germany, and the JSPS Fellowship, Japan, and has been a visiting faculty member at institutions worldwide. Dr. Rao has supervised 30 PhD students, published 325 research papers, and holds 25 patents with 5 technology transfers. His work on diamond coatings won the top prize in the Prime Minister's Dare to Dream national competition in 2019. He also leads a startup at IIT Madras Research Park, focusing on innovative diamond technologies for applications ranging from semiconductors to electronics. Dr. Rao's contributions exemplify excellence in research, innovation, and education. Without further ado, I'd like to invite Dr. Rao on stage.
Thank you very much for the nice introduction. And hello, very good afternoon to you all. Had your lunch? Yeah, that's good. All right, so that's the title of my talk, Indigenous CVD and HPHT technologies that we're working on at IIT Madras. I'll take you through a small journey of what we have been doing since the past 2 years, but also with a little introduction to how we got started with our diamond research that we have been into for the last 2 decades. So I have my team members here. I'll introduce them shortly. So I'm a teacher. I teach in the physics department, and I belong to about 4 to 5 different centers, including one of the latest ones, that is India Center for Lab-Grown Diamond Research, funded by the Ministry of Commerce and Industry. Okay. All right. So let's Well, I think information about my team members would appear in the next slide. So what is the background and motivation here? Well, as you can see here, India imports both natural and lab-grown diamonds for cutting and polishing. Very often, as a scientist, people ask me the question about what is the difference between the natural and lab-grown diamond. For us, there's no difference. Both are diamonds. Nature produces crystals. Diamond is also a crystal. Nature produces quartz. I can also make quartz in the lab. Any gemstone that you get it naturally can also be made in the lab. So to that extent, there is absolutely no difference between diamond that is grown in the lab, and I would say once you call lab-grown diamond as LGD, the other one we should call it as NGD, nature-grown diamond, right? Nature grows diamond. It's the biggest lab we have. We're all living on. All right. India, of course, is number two in producing diamond. We know that any diamond mined anywhere in the world has to come to Surat, no? Cutting and polishing. I've seen these really excellent hands, experts that could bring in all those 58 facets on even on a tiny 1 millimeter cube of a diamond crystal. But then we are number two in producing diamond, but a distant number two after China. So as you can see here, LGD is, we only have about 15% of market share compared to China that has 56% of market share. That's a huge thing. That's because, while in India we focus a lot on chemical vapor deposition, CVD grown diamonds, China does focus on HPHT, high pressure, high temperature, and that technology is zero in India. So we are trying to develop that. So the whole idea is we must be self-sufficient in developing our own technologies, indigenous technologies, to meet these big demands of producing diamond, right? So there's an urgent need uh, for a center of excellence to grow diamonds in the lab. That's how our center, the new center has originated. And you can see here, lab-grown diamond jewelry market is expected to increase worldwide by uh, $5 billion by this year, which is supposed to go up threefolds by 2035, another 10 years. So that's the kind of potential you have in lab-grown diamonds. All right. So what we have here is yes. So we have been working on what are called diamond coatings. I can coat diamond as a thin layer, and as you know, diamond is the hardest material, and it has a lot of mechanical applications. In fact, we can list about 20 different applications of diamond: mechanical wear-resistant coatings, biomechanical coatings, and radiation-resistant coatings. It's a wonder material. So this is about one of the awards that we won, an award that was instituted by our Prime Minister in 2019 from about 1,200 entries from around the country from different labs. Ours was chosen as one of the 12 entries, and then from these 12, we were adjudged as number one in the country. This was based on the technology on diamond coatings that we have been working on since 2 decades, right? So we told that this coating technology could be useful for our hypersonic missile technology, right? Okay. And then, well, 2 years back, we were approached by the Ministry of Commerce and Industry. And then when we came to know about what they wanted it from us, we got interested being researchers, working in the area of diamond growth. We thought that it's very exciting to get a huge grant to do research that we can take it all the way to product development. I'll explain all that in the next half an hour or so. And of course, as researchers working in institutes like IITs, universities, we get funding from various agencies. But then this is the first time that an announcement was made in the Parliament session. This happened last year, last year. That also shows the importance attached to uh, indigenous diamond growth in the country. This initiative seems to have come from our Prime Minister. He wanted to make India number one in not only cutting and polishing and producing diamonds, which I think is a great move. So our center focuses on those five different verticals that you see there. One is most of you know about how diamonds are grown using microwave plasma CVD, right? And we are in the process of making our own indigenous CVD technology. And when you have a microwave CVD unit, right, and you need a power source for that. And this is typically worldwide, most of the companies that sell CVD generators, they use a magnetron-based microwave generator, 6 kilowatts, 20, 40, 50 kilowatts. And magnetron ones are okay. They work for 1.5 years, but efficiency-wise, they're not the best. So we are going by what is called a semiconductor-based power generation. This is called SSMG, solid-state microwave generator based on gallium nitride technology. And the third biggest challenge is the HPHT, high pressure, high temperature. You may want to know that Russia developed this HPHT technology way back in 60 years ago. And they've transferred all the technology to China. And China has been making HPHT machines left, right, and center. And the top 10 companies in the world that produce HPHT are from China. And why China is doing that? And some of these companies, they produce these HPHT machines like mushrooms. If you go through any of these websites, you will see hundreds and thousands of these machines. Each HPHT machine is about 80 to 90 tons, right? Because you need, look, diamond forms 80 to 100 kilometers below the Earth's crust. At that level, right, you have, of course, the pressure, enormous pressure, and you also have temperature, and you have carbon source. Imagine replicating that in the laboratory. So that means I need to bring that pressure at the lab level. And what kind of pressure is it? Our body feels 1 atmosphere. And we need 50,000 atmospheres for that. 50 to 60,000 atmospheres. That's amazing. And then, and you need these strong hydraulic systems. And China has mastered that. And when we agreed to take up this challenge also of building HPHT along with building the other things, the biggest challenge is we need an Indian partner company that would build those hydraulic systems for us. And we have a lot of talent in the country. There's no dearth of talent. We could find a company that now working with us closely. We are building the indigenous HPST machines. It will be a reality probably in another 2 years. We got a prototype machine built already, but then that is initially we'll be using it for understanding the processes and from all the parameters that we derive from the small unit, we'll apply it to making the bigger one. And then the most important thing is having an analytical lab, right? Most of you in the diamond business also must be using some analytical tools, but you need some advanced level tools. I'll tell you why you need those advanced level tools. And then we are also, one of the mandates of our center is to train people and tell, more than what people would normally know about the quality assessment of diamond. So this is our wonderful team. We have 5 faculty members. A venture like this requires a lot of expertise. I'm a materials physicist working on materials, crystal growth. I have my 2 colleagues who are here, Professor Arnachalam and Professor Satyan. They're from a very strong mechanical engineering background, right? They're in the team. And the other 2 colleagues are not here, one from electrical engineering and one from my own department, physics. Okay. And then we have a strong team of nearly 70 people. Some of our group members are here. And, we are very happy with the progress that we have made in the last 2 years. This is something that I want to tell all of you, where we lag behind in India. we have a lot of research going on in various universities, places like IITs, right? And of course, a lot of business on the other side, and industries are there. But there's always a disconnect between industry and academia in this country. Look, technology doesn't come from the heavens. It is all lab grown, right? I take it to certain level, and what academia, what we do is that disconnect means, I do my research, I do my teaching, then we end up everything in the form of publishing papers, and probably a few patents will come. And that's where we are. And industry has always, in India especially, has an inhibition to work with us closely, right? But this gap, in one way, is closing up, closing in our institute. IIT Madras has taken a big lead in establishing what is called a research park. You should all visit this place. We're also organizing. I'll give you information about it in next month. You'll get a chance to see all this, and also our the wonderful research park that has such a great ecosystem that allows lab-grown research to be taken to the level of industrialization of products, right? And some of the examples are, we have the Ether Energy. It started with 3 students and 1 faculty, and Ether Energy is now a company with 1,000 people. They're rolling out all EV two-wheelers, and they're launching into electric vehicle cars also, right? So what it says is most of the research in lab-grown diamond around the world, if you see, all of that has come from universities, right? Starting from the United States, you see Oak Ridge, Oregon National Labs, Carnegie Science, and so on. And if you look at Europe here, and all these, Fraunhofer is a leading institute working on diamond and diamond-related coatings. University of Bristol, CNRS Labs, all of them focus on research, and of course, industries benefit them from what they're doing. They collaborate with them and take the technology to the next level. Japan, of course, is a leader. Japan, we know, is a leader in doing lab-grown diamond research for many, many years. Russia, of course, has a lot of collaborative work going on in Russian universities. China also. And India, probably this is the only lab that is directly working on product development based on lab-grown diamonds, right? So, yes. So you all know that we go here in this beautiful arena, glittering diamonds everywhere, right? Since yesterday, we've been seeing all those diamonds of different carats, right? But what you may not know is the diamond as a gem crystal is only one small part of the story. The real story is diamond has about 20 different applications, and some of them are listed here. I started with hard coatings. When you have a tool that is coated with diamond, you can increase the lifetime of the tool by 15 to 20 times. That's a patent that we have, and that of course, Germany, Switzerland have developed these technologies, and Diamondtronics, one of the most important applications of diamond is today we are using our electronic devices, our mobile phones, our laptops are used throughout the day, non-stop. There's a lot of heat generated there, right? And what happens to the heat if it stays in your device? It'll start destroying your electronic components. So this heat has to be dissipated out. There are what are called heat sinks. They're standard heat sinks, but nothing like a diamond layer. Diamond, it's an electrical insulator, but its thermal conductivity is 5 times more than that of copper. If someone comes home, if you want to tease your guest, give your cup of coffee in a copper or silver teacup, what will happen? We can't hold it because these copper and silver are the best thermal conductors. But you may think that, let's say you manage to make a cup out of diamond. Diamond is an electrical insulator, but diamond's thermal conductivity is 5 times more than that of copper. That means it can be used as the best heat spreader. So most of the electronic devices in future would use diamond as a heat spreader. You have seen that there. And it's in for some of these very high-tech applications, like in X-ray windows for space applications, what CERN uses is transparent windows made of a diamond, because diamond is a radiation-resistant material. When you have gamma rays and X-rays impinging on diamond, it is not damaged. It's not the case with other materials, right? And one of the societal works that we are doing is, I don't want to go into the details, the coatings that we do on electrodes, you can also make diamond to conduct by doping, right? Okay. And the two applications. One is nitrogen doped vacancies in diamond are going to be the uh, no materials for next generation quantum computing. We are all talking about quantum computers, which will be, you know, a million times faster than the classical computers. This will be a reality probably in another 10 to 15 years. But you need there's a lot of nice physics and materials physics is involved there, replacing carbon with phosphorus and other dopants. But one of the societal applications that we are looking at, when you are in the campus for this workshop, you'll know more about it if you want to, is to use those electrodes to purify water. You know, water contaminated with um, pharmaceutical waste and textile waste is always a big problem. We all like wearing colored dresses, but what does the industry do? They start dumping all the dyes into water bodies. We are contaminating water bodies big way. And diamond electrodes can treat that by electrochemical process. We need medicines, but the problem is, you know, the medical effluent is also let into water bodies, and that can be treated with electrolysis process using diamond electrodes in a very effective way. All right, and so beyond gems, that's what the heading that we are given. So GEMS is only one part of the wonderful applications of diamond. You see, all next generation technologies are all going to be based on diamond. You have silicon and diamond for AI and cloud computing. For the next generation 5G, 6G technologies, you need gallium nitride devices on diamond, silicon carbide and diamond for power electronics. No, for all future power electronics, high frequency, high voltage applications, you need diamond, right? And diamond for NV centers for quantum computing, I mentioned, and beyond, the higher end technologies. And Japan has already had diamond as a semiconducting material. When Japan declares a material as a semiconducting material, they go all the way out making devices out of it and sell those devices to the world. They don't let that material come out of the country. But you may ask me, what is the big deal? You know, we are all making diamonds. So if Japan is not letting others buy the diamond, what is the problem? We have so many diamond here. But we are not talking about small stones. We are talking about wafers. You know, for electronics, you need the material in the form of a thin wafer with a radius of a diameter of anywhere from 4 to 6 to 12 inches. That's how the silicon-based technology has grown. All that we are doing in all our devices is silicon-based wafers, right? Now, silicon wafer has started with 1 inch wafer. Now the technology has grown to 12 inches. This took 30 years. But then somewhere we have to start with diamond also. Today we are able to get 1 inch square wafers easily, but for industrial grade production, for companies to use mass producing devices, you need large area wafers. This is going to be possible in a couple of years. Yeah. So what are our missions and goals in our, so it's called INCENT LGD. Please remember this name. INCENT LGD stands for India Center for Lab Grown Diamond, right? So to make the country, our country, number one in lab grown diamonds for gems, and not only gems, for electronic applications also. So Center of Excellence is being established. So the most important thing is, if you ask me what is the difference between the quality between a gem grade diamond and a semiconductor grade diamond, both are diamonds, but in terms of impurities, there's a lot of difference. The impurity levels in a semiconductor grade diamond have to be parts per billion, which is not the case when you're talking about gem grade diamonds, right? Still, with the kind of impurities that you have in the gem grade gem crystals, You can still certify it as a gem crystal, but that's not good for your electronic applications. So you need to minimize those defects, right? So that's where the recipe development plays a very important role. Absolutely important. And I talked about this solid state microwave generator development. And so we are in the process of, um, uh, you know, um, inventing our own designs uh, to come out with microwave plasma CVD and high pressure, high temperature process. Yes. So what China has been doing since 60 years. This is the capability of what we can do in our country, right? With our strong group of nearly 5 faculty members, experienced members, and about 60 people, who are all funded by this project. We pay them, and see, this is a already in 1 year we could come out with a prototype model of HPHT. Yes, and this prototype model is it's about 1/5 of the total size of the actual one, and this is to initially understand all the processes. Using that information, we give feedback to this industry that is building these hydraulic systems, and then it's not a one way of coming out with technology. It's all mutual. We work together with industry, and I think within the next 1 year or 1.5 years, you will see the bigger machine also. And in a similar way, we are completely indigenously worked out on our own design to come out with a CVD machine. The whole idea is CVD machines you can buy in India. Some of you must be using it. But then most of the machines that you buy, they do not come with any recipe. You just buy and the seller will say, hey, you paid 90 lakhs or 1 crore, but then I don't have any recipe. This you have to develop on your own. And recipes have to be developed scientifically, right? And I think the crux of the whole thing is it all boils down to getting the right kind of recipes for diamond growth. Not only gem grade, for gem quality also, the recipe is important. Otherwise, your overall yield will be very less, right? You're using 20 machines, and let's say, and then you have 25 millimeter square seeds inside, and let's say the growth happens properly only on 50% of them. So you're wasting a lot of your resources, energy, power, everything, right? But if this 50% has to become 80 to 85%, and that requires proper, recipe development and use of proper gases, pure gases, and all that. All right. So we have a beautiful campus. How many of you have seen IIT Madras campus? Oh, just two, three, four, five, six. Not many. So you should all visit this campus. It's one of the best institutes in the country and one of the most beautiful campuses. All right. Uh, this is a Google picture of our campus. That's our center. This is a central workshop where we are building our HPHT lab. We call it the Diamond factory, right? Because it needs a very solid foundation. Because each machine weighs about 80 to 90 tons, right? We also got two commercial Chinese machines which have not been installed yet. By the way, the Indian government has completely banned the import of Chinese machines anymore. You cannot import Chinese machines, number one. China itself has taken a decision not to sell anything related to diamond to the rest of the world. They want to make all the money out of the business they do with diamond. That's it. So indigenous development is the only way forward. And yeah, so the main center, the SSMG development place, the HPHT labs, all these you can see if you visit the place. I think I'll skip this. The way we started now, we have that video is not there, I think. It's fine, it's fine. Okay. Just to give you an example, some of you must have seen this. This is the Chinese machine. It weighs about 60 tons. Because, it's not easy to get that kind of pressure. And you have 6 hydraulic arms, but the action takes place on just a small cube, which is 80 millimeter cube only. So the diamond growth happens there. But to get those kind of pressures, you need an equipment of that magnitude, right? So what we do is we have teams that use simulations to evolve with a model which is not the same, because we are not reverse engineering. Everything is from the basic fundamental principles all the way to realizing the final design. And so there is no copyright violation problem. This is very important. If you just reverse engineer and put a machine, you can't even show anyone, because the person can sue you saying that, hey, I saw this machine somewhere, and why did you copy it without paying the royalty? Right? All these issues are always there. Okay. Our analytical facility that we have established, well, we have, even in our regular center, Material Science Research Center, we have very good analytical facilities. But in the new center, we have got additionally a few more. And then why few more? This is because I mentioned in the beginning that to grade a diamond as a semiconductor grade diamond, right? It goes beyond 4 Cs. These 4 Cs are good for grading your jewelry diamond, no? The carat cut, clarity, and color. But if you have to declare a diamond as a semiconductor grade diamond with parts per billion or less defects, you need various other techniques like micro Raman, PL, cathodoluminescence, FTIR, and high resolution X-ray diffraction. All these facilities we have there. And if you want any help in analyzing the quality of the diamonds that you grow, you're always welcome to visit us, right? All these facilities we have. By the way, we have a stall here. Uh, I don't know if that number is there. This is a part of the GJEPC's main stall. This is a stall dedicated to showcase all that we are doing in our center, in Central LGD. Probably you get the information from the GJEPC counter there. Yeah. So what is the current scenario? India is good. There are many players here using microwave plasma CVD to grow diamond. These are called roughs, you make roughs. But we have also seen that some of them get machines from various sources. They don't get recipes. They start using them without bothering about the purity of the gases they use, which is a very crucial step, number one. Number two, the quality of the seeds that you start with also has to be very good. So there has to be an initial quality assessment of the seeds that you use before you go start the growth, and this is required to enhance the final yield. You don't want when you place 21 seeds like this. Let's say you're able to grow good quality diamond only on 50% of them. It's not going to serve the purpose, right? I want as much yield as possible. So right now, there are no application-specific tools available for diamond growers, I would say, and it's only just goes by visual inspection. You buy, and these seeds are very expensive. We are buying these seeds right now. We start producing our own seeds. You buy a small 1 centimeter square seed. You know that it's anywhere from 12,000 to 18,000 rupees. And the person who is selling it, he would say, yeah, these are good quality ones. And how do you quantify that, right? That is not there. And you go by trial and error method, it's time consuming. Today you might get 70% deal, tomorrow you might get only 40% deal. It's not going to serve any purpose, right? Yeah. So there are expensive factory loaded recipes, no seed quality checking. This is absolutely important. And no process gas flow and purity control. This plays a very crucial role in determining the final quality of the diamond. Also, people ask me, we have so many CVD machines with us. Can we just go ahead and use them for creating semiconductor grade diamond? No, you can't do that. a lot of research is required in order to realize semiconductor grade diamond. It depends on the kind of power you are using, the power stability, the temperature stability, and the purity of the gases that you're using. So it's not that just having a machine will ensure that you'll be able to grow semiconductor grade diamond. No, it will not happen. Okay. This is just an example of what we have done in the lab. You buy these seeds, put them, because this is a plate where the growth happens. You know that in a microwave plasma CVD, there's about 3 inches. I can pack as many as 21 seeds, right? And seeds you get from different sources. And this is what, at the end of the run, this is what you'll see, right? The carbon formation, their inclusions, they're hardly half the pieces that are useful as seeds with better yield. The rest of all, you have to reject them or you have to cut them and polish them. And this is all also very energy intensive, right? So less than 50% qualified product ratio. This has been the case from the literature that we have found with all the CVD machines where recipe development has not been given a proper focus, right? Yeah. So what is the way forward? Of course, our indigenous tools, MPCVD tool, which is in progress, a lot of research is going on. What we want to, what we can, so we also use diagnostic tools. OES is a very simple but very important optical uh, analysis parameter. Um, and then we want to scientifically document these recipes so that you can reuse them. And you need to have application-specific substrate holders. This is also a very important parameter. And then um, you need internally certified seeds, and this is a very important factor. That is, you have to use high purity gases. What we have seen is people ask us that, look, I put so many seeds, and in order to enhance the growth, you have also a lot of nitrogen inside the growth chamber. That'll give you a quicker, big seed within short time. But then you're putting so much of nitrogen inside it is brown colored, of course. And sometimes deep brown, sometimes it's black. And then you say that, okay, we can treat them in HPHT, right? Put it in a HPHT unit for treatment, but then you're only dispersing those defects, you're not removing them. So the quality, the final quality will not be as good as what you're supposed to get to call diamond as a semiconductor grade diamond. All right. And look at this, what we have done. This is just an example of, by taking care of some of these points, right? By looking at the initial quality of the seed, by making sure that we use a proper high purity gas, you see that all the seeds that we use turn out to be turn out to grow good quality diamond on them. So the yield is almost 90 or more than 90%. That's what we need finally, right? Yeah. So the MPCVD machine that we are making will also give you a turnkey kind of a facility where you load the seeds without any hassle. I mean, we have a program whereby we even want to assess the quality of those seeds that can be used in the CVD reactors. So you just have to take those seeds, put them in the reactor, and grow them, and try to get 90% of yield. Yeah. In fact, some of the recipes that we have developed are working out to be so good that even if when we start with a bad quality seed, mother seed, by optimizing our recipes, we are able to get good quality layers on top of that. That's what we have achieved in the last 1 year. Right? So all this I'm saying to emphasize on the point that recipes play a very, very crucial role. Yeah, so the complete solution, if you see, there's not a single point solution. All these things are required. The growth recipe for different quality of diamonds. There's no single solution for growing gem grade diamond, optical grade diamond, and semiconductor grade diamond. You need to have different growth recipes. And quality of the grown crystals has to be checked all the time. This is absolutely important. Post treatment has to be done in a judicious way. Of course, you need to have a proper CVD technology selection guide. And I mentioned about the importance of gas purity and all that. Of course, color diamonds, we are also seeing vivid colors here, beautiful colors. And colors can be obtained by two ways. Any crystal that is colored, any gem crystal that is colored, color comes because of defects inside. A pure diamond, shiny, white crystal, when it becomes colored, that means it has defects in them. And that means you're making these crystals a little impure but that impurity gives you a beautiful color, it's okay. So you need to control them in a way that the original diamond structure is not lost. So let's say I take a piece of diamond, put it under high energy gamma rays or electron source or X-rays, right? I create defects and those defects will make diamond colored. But then you need to control the radiation damage in such a way that you do not lose the basic diamond structure, right? This is very important. So we have tested some of the colored crystals, and to our surprise, that there is no diamond structure there. That means whatever has been done it is done to the extent that the diamond structure is completely lost. This is where you need our help, scientists' help, right? Okay. So um, we have also coined a term called diamondtronics. You know electronics, right? Right? All electronics. So the future electronics that are going to be based on all diamond-based electronics, we call it diamondtronics. For that, wafer scale diamond characterization is, of course, absolutely essential. We can do all these characterizations. This is just a simple example to show that even when we start with a seed that has some coloration there, using our recipe, we're able to get better quality diamonds, which is good, right? But imagine if your initial seed itself is of good quality, if your initial seed itself has a transmittance of 73%, your final quality will be much better with lesser defects. Okay, that's what uh, I want to convey it here. And see, one thing you should realize is we have a great potential. India, the kind of diamond growth that happens in our country, we can be the world leaders, not only in producing gem grade diamond, but also semiconductor grade diamond. We have the brains, we have the resources. We need to channelize them in a proper way. This is where academia and industry have to work together, which happens in all the other countries. For example, the three major companies that produce the so-called best quality seeds. Most of you know, most of you using CVD growth techniques, I hear that where do you get the seeds from? The best seeds. I don't hear the name of any Indian company. You always say that it's Element 6, which is a company from the US, EDP Japan, or there's one more company, the Diamond Foundry. That's it. We are not naming any other company from India. Why? That's because we are not paying attention to these quality improvement factors. If we focus on that, we could be the country that can produce high quality diamond seeds for semiconductor grade applications also. So let me again tell you that it's not just sufficient to have a machine. You also need to focus on all these points that I've been mentioning since the last 25 minutes. So um, in fact, the growth recipes that we're using with the existing microwave plasma CVD, we are able to get the qualities equivalent to that of what Element 6 is producing. And Element 6 sells these at a very, very high cost, premium cost. Because they also know that they have established the quality factor, and then they know that people would come and buy from them. We want to grow best quality diamonds, not only gem grade diamonds, but beyond, that's semiconductor grade. We have been developing something very unique. Our team is here. This is, we told the ministry and GJPC last year that this is almost 1.5 years of research. Marking is done on diamond, right? When marking is done with some light source, there's a possibility of damaging that part of the diamond. If you go through the scientific literature, you find tons of papers that show that, yeah, the marking is done, but surrounding the marking, the diamond structure is all gone. And whether the diamond structure is retained or gone, we can do a few tests and find out if that is the diamond structure is there or it's gone. In most of the cases, if you don't optimize the parameters that are used in that optical source to do the marking. There are some companies that are marking. Now, major companies around the world want to do this marking. They want to etch their names, their company names, and so on. But ever since we have been developing the good quality seeds, we've been telling the ministry that there's one thing that is missing is these seeds come without any certification. Right? I ask the person, he'll say, yeah, these are all good quality ones. There is no proof for that. How do you quantify that good quality? That's what I said. But if you buy seeds from Element 6, this US company, or from EDP Japan, right? The batch of samples that you buy, let's say 10 of them, you get a certification for the entire batch, but not for individual seeds. We have created something unique here. If you have your phones, you can scan it and see what you get, right? This is fantastic. This is done in two ways, right? One is you can create a barcode on the surface and in the subsurface also, about 300 microns below the surface. Because one of the things that we were told was whatever marking is done on the surface of diamond, it could be erased out. You take it, polish it, and it's gone. You don't know you get nothing, no information about it. So we have managed to write all this information, create a barcode or anything we can write. 300 microns below the surface of the diamond. It's not easy, right? So if you want more information about this, meet our colleagues, Dr. Indu and Ritu in our stall there. Sagarika is not there. Okay. Right? They'll tell you more about it. We have a stall there, and they can explain more about what we are doing. And there's a startup even on that. That I think soon. What I heard was uh, both natural diamonds and lab-grown diamonds will be required to be marked. And if natural diamonds and lab-grown diamonds are not marked, they'll be called synthetic diamonds. That means probably without marking, they will not have any value. And seed marking is absolutely required. So when we are supplying a seed, right? And if I say that this is a semiconductor grade seed, imagine you have a barcode like that. Did you check it? Yeah? You get all the information. What else you want? Right? It's good, right? Yeah? All right. Yeah, okay. That's what you get. You must have got it, this one on your mobile phones. See the technology. So that one looks like a small speck on on your seed, which you can see in our stall. They have a small microscope. What looks like a small speck is actually a barcode. So we can engrave anything, and the diamond structure is not damaged here. That's the most important thing. Diamond remains as diamond. Somebody asks you, hey, what is the guarantee that diamond remains as diamond? We can do tests to prove that this marking doesn't damage the diamond part of it, which is retained. Not easy because this takes a lot of research effort, right? I think you should clap for our team for achieving this. Okay, good. Now, hey, this is a lot of work in the last 1.5 years for us. And you see my two colleagues here, they're strong people from the mechanical engineering department. And we have been, so this is the prototype model that is, it's only the 1/5 of the size of the actual machine, which would weigh about 80 tons. This is a prototype machine, 1/5 of the size. But we wanted to build this to make sure that HPHT machines can be built in India to start with. It's done with 1 year with our research efforts, working closely with this industry. The industry makes the hydraulic systems. And but there's one more thing. Why do you need high pressure, high temperature units? Going back to the example of China, China is producing top 10 companies in the world are from China. And they're doing it with a purpose. The industry grade diamond is all produced using HPHT machine. These are powders, starting with micron size powders all the way to millimeter size powders. They're also HPHT grown diamonds are also used in jewelry, but in abrasive applications, mechanical abrasion parts, right? We have the numbers somewhere, right? Uh, we got the numbers from the ministry's website. It shows that in India, for industrial applications, 1.25 crore lakhs crores of crores worth of diamond powders are imported every year. All this is coming from China because in this industrial grade diamond, China has 95% of the share. That's the reason why they're focusing so much on HPHT. And we cannot buy those machines anymore because we develop them. And you can all invest in putting up thousands of these units. It's not a problem. Right? And HPHT machines are also used for treatment. Treatment is a small process. You grow diamond using CVD and then transfer it to your HPHT machine. Treatment is a 3 to 5 minutes process. It's not a big deal. But if you want to grow a big diamond in using a HPHT process, it's exactly like CVD. It takes 10 to 15 days. And the most important component here is, or bunch of components, is what sits inside the hydraulic system. There's a small block. It consists of about 15 different parts, carbon inside, some metallic powder, and it has to be heated under that pressure. So that's called the cell, supercell. We do not have the supercell technology also. China gives you the technology if you buy 30 machines, and they even after buying 30 machines, they won't reveal everything about the recipe. They'll just train you how to load a ready-made cell and get the growth done. That's all. So our teams are now developing, you know, the entire supercell. We want to indigenously develop the supercell also along with the machine. That's the most important thing. This machine gives you the required pressure, and the temperature comes in the cell. Unless you develop the recipe, that's where the crystal growth part is very essential. So we're also when we develop the microwave plasma CVD, there's no reverse engineering here. We start with basic simulations and and designs are evolved, and then we get them fabricated. And again, within 1 year, we have shown that we have started seeing plasma in our own indigenous systems, and we'll try to incorporate all possible sophistication to get the best possible indigenous MPCVD machine, and probably this will happen in another year or so. Okay, so I don't want to go into all these details about how the simulation is done. We have a team that is completely dedicated to the simulation work, not only MPCVD chamber simulation, simulating the cell part, supercell part for the HPHT machine also. Yeah, very briefly. To run the CVD machine, I told you a magnetron power supply is used, and we are going in a different route, trying to produce a microwave, solid-state microwave generator using gallium nitride-based devices. This is not available in India, and only few companies around the world make this device. In fact, the few CVD machines that we procured from standard companies, we also have 4 commercial machines that we bought in addition to what we are developing. These machines we use to understand the recipes, right? But these companies said that, look, we don't have resources to evolve with a new microwave generator, and they're in fact ready to collaborate with us once we come out with our own system. And this will also happen probably by next year. But once you have a SSMG generator, solid state microwave generator, then you can have basically um, the efficiency of your CVD machine will be much better. Okay, I think I'm running short of time now. That's a commercial. A few points about HPHT. The growth, it's used for growth treatment as well as industrial grade one. And we have taken up this challenge. And I'm sure that what China has been doing since 6 decades, we made a great progress in 1 year itself. And I think it's a matter of 2 more years of research and development, and we'll come out with our own HPHT machine. Yeah, I think I can skip this. Yeah, these are you see that a supercell consists of so many parts, right? You can see that cube, and you're applying 6 gigapascals with 6 hydraulic arms from 6 sides. You can build building an hydraulic system is one part, and making that cell is another part, and making it work is another part, right? A lot of research is still going on the growth aspects of diamond using that cell. Yeah. Yeah, this is our prototype model. Yeah, technology transfer and commercialization also we are looking at. We have basically three startups. One is Kapindra that deals with all the coating technologies that we have developed. The Diaseed is the Diaseed deals with creating best quality seeds, and Diastra is for marking diamonds, right? So you can get to know about these startups from our stall there. This is Incent LGD stall. We also propose to have, this is one of the mandates ministry has asked us to do outreach programs. From your companies, industries, you can send people for these short-term programs. We'll very soon announce it on our website. We want to do it probably once in 4 months, a 15-day, 10 to 15 days training program to all your scientists, employees on various aspects of diamond growth. Right? Yeah. Yeah. You can skip this, yes. And finally, yeah, this is Vajra Industry Research Academy Meet. It's a one-day workshop we are organizing in IIT Madras, right? Please register and come. It's a one-day packed event starting at 9 o'clock in the morning all the way up to 5:30. You can come the previous day, stay in a hotel and start attending the sessions from 9. There, as you can see here, there are um, 4 panel discussions, right? Yeah, yeah. So you get this information from the website, and you're please welcome to register and attend this one to get more information about all those aspects beyond gems, next generation applications, diamond quality checks, lab grown machines and process equipment, what Incent LGD offers to Indian LGD industries, makers, and entrepreneurs, right? Please do. Thank you very much. Yeah, yeah, please. Questions always we want as teachers. Exciting, right? Yeah?
So, Professor, I had a question. So, HPHT versus CVD,
Yeah.
in a lot of cases in gem quality, HPHT, when you test it with a diamond tester, it tests as a moissanite, while CVD tests as a diamond
Okay.
in a lot of cases. So, a lot of clients, especially internationally, they prefer CVD because of that. So, is there, yeah.
No, but if you're growing diamond with HPHT or CVD, once I see the diamond structure, it's diamond. Moissanite is different. So if you're looking at Raman spectroscopy of moissanite and diamond, both give a similar peak at 1332 centimeter inverse. So that's not the right test. So you need to look at the band edge, what is called the band edge. The band edges are different for both.
In terms of hardness, is there any difference?
This question
Yeah.
was asked by many. They say that the hardness of HPHT diamond is lesser than the CVD one. That's why we don't think HPHT is a real diamond. You know why that happens? Diamond is the hardest material. Its hardness is 10 on the Vickers hardness scale. Now, HPHT is grown with a precursor, with a metal precursor. It's colored because these metals are incorporated inside. To that extent, you lose some hardness. That's it. Otherwise, you do a simple test, UVV spectroscopy, Raman. Once I confirm it's diamond, it's diamond. And these people are very strong. Once she says that it's diamond, it's diamond. Ritu. So she says her question is similar questions she had. What is better, HPST or CVD? I think both the same. Both, there's no difference. Everything is diamond. So I told you the HPHT process with this high pressure. Hmm? Yeah, yeah. So I use it to enhance the color of diamond that is grown with CVD.
So HTHP enhances the color of the diamond,
Yes.
you say.
So because the CVD process uses gases. These
Mhm.
gases incorporate defects in the crystal. So
Okay.
in order to, those defects make it colored.
Okay.
So to enhance the color, to remove the color, you need to give a treatment. That's a standard process. And you can also put in color using HPST.
HPHT.
Yeah.
Okay.
But more than that, HPST is used to create industry grade diamond. The grid, it is called the small
The
particles of
smaller
diamond.
diamonds.
Yeah, which you can't do with CVD process.
So what do you suggest? Like it's the same.
It's the same.
So if you want to buy, you can buy any.
No problem.
So if the smaller diamonds, then the HTPT is better. Or the CVD, the bigger diamond, nothing.
That doesn't matter. No. Diamond is diamond.
So if you want to
Hira,
go for a
hira.
bigger, better color, then go for HTHP.
Yes.
And if you want to go for a natural looking thing, then go for CVD, something like that.
No, natural looking either in CVD or HPST, it's okay. But what I'm saying is, if you have a colored diamond, you better ask the person how the color is obtained, whether it is through doping method or irradiation.
And what about the pricing between the same?
That you have to ask our young businessman here.
No. It does it matter the pricing for the?
Oh, okay.
That's what.
Okay, the lab grown diamond is almost half or one third. What man? One third. One third.
No, I'm comparing between HTHP and CVD only. The pricing between these two. Does it matter?
So the pricing in CVD in smaller size diamonds will always be higher because it only comes out from the tops that come out of the diamond. But HPHT in the smaller sizes is cheaper, and in the larger sizes, CVD is cheaper.
So let me put it this
In
way.
pricing,
Until recently, uh, the larger or smaller size diamonds are all made by HPST. CVD process has evolved in a big way, and it's much simpler and easier. People have shifted over to CVD to create large-scale gem-grade diamonds, which are much cheaper than HPHT diamonds. So if you want to buy yes. So if you want to buy a diamond, I think you should go and buy lab-grown CVD diamonds. Yes. Now, um,
I just wanted to know, so does that mean all CVD diamonds need to be done that HPHT treatment to get that white?
mostly. So
Oh.
if you are using that CVD process with a large amount of nitrogen gas, it makes it brown colored.
Oh, so after that they do
if you want to
HPHT.
use as is as a brown or yellow colored diamond, it's no problem. But if you want to remove the color, you have to treat it. So if you want to grow a pristine one, you grow it with pure gases, so no incorporation happens, no coloration happens, but that is time taking. So
So there could be diamonds which is a combination of CVD and HPHT.
yes, yes. Or I can grow a good crystal using CVD process itself.
Oh. Thank you.
Yeah. Yeah. Then it depends on what kind of diamonds you're looking for. Is it for?
Now, what is the future? Future for just you told us it would be for semiconductors and for other
For
purpose.
semiconductors, you need wafers.
Okay.
Only CVD is the solution.
CVD is the solution.
For gem grade, China is producing gem grade diamonds using HPHT, tons of them.
Okay.
In India, our people do use CVD,
Okay.
right? But HPHT is required for industry grade diamonds,
Oh.
the grit. Yeah.
Okay. Okay.
But semiconductors, only CVD.
Only CVD.
Yes.
Okay. Thank you.
So recently there was a documentary on this Netflix platform, which talked about nothing lasts forever, and there is a new technology which they talk about, which is evolving in Korea, where that is an alternative technology to HPHT as well as CVD, where diamonds can be produced in much less time compared to these two methods. So, are you also researching on something similar, or?
Yeah. We have seen those reports of even producing diamond crystals from plastic using laser, These processes are all known. There are different ways of producing diamond, but then you can't get big enough diamonds. These are all tiny particulates you get, right? I think what the Koreans have done is using a metal precursor. You normally use a metal precursor to reduce the melting point so that the growth can happen at a lower temperature. But we have tried in the lab, you can't get big crystals. That you see tiny diamond crystallites in the growth oven. Yeah.
So one thing what the ministry highlighted last year was when they released this, funds to IIT for research, they also said that, it will bring down the cost of producing these diamonds drastically over a period of time.
I think our business fraternity, if you ask them, the prices have already come down because even in India, there are diamond business houses that have hundreds of CVD machines. They're producing diamond, but that's what I said. One is the cost of diamond is coming down. But I think people are also looking at other applications of diamond beyond looking at it as a gem crystal. That's where, purity, semiconductor grade diamond, making it into wafers. Even with the existing chambers, you get about 2 or 2.5 inch circular wafers. But then for industry grade electronic applications, you need bigger ones. That's what I said. Silicon started with 1 inch wafers. Now the technology has grown to 12 inches. It took time. But then somewhere you have to start, right? Then you need to have bigger machines, more power to produce large scale wafer. But the problem here is diamond grows as diamond only when you have a diamond seed. I can't have a 6-inch diamond seed to grow another 6-inch diamond on it. That's a big challenge. So are there any alternatives? Can I grow a 3-inch diamond seed on some other material? That's what we are researching.
So just one question, just to sum it up. A large part of the market believes that CVD is of a superior quality as compared to HPHT. Is that actually the case, or they are both the same in terms of quality, in terms of gem quality?
Gem quality, I think so, because if you're using HPHT without those metal precursors, you don't have the problem of incorporation of these metals into diamond. That will reduce the quality of diamond. So you need to, if you want to grow a pure quality diamond in HPHT, then you should not use the metal precursor, which means the growth temperatures go to almost 16 to 1700 degrees centigrade. That again is a big challenge. I think Europeans are doing, Russians are also masters in growing big crystals of diamond in HPHT, Because the advantage of HPHT growth is the diamond that grows in HPHT, it comes with natural facets.
Okay.
Not as many as a normal diamond would have, but it has the growth. It is called the crystallography. The crystallographically, it grows along with those facets. But the one that you grow with CVD process, it's like a slab. It's like a thin slab, like, you know, like this one, right? Like this one.
Okay.
Then you make the facets. So there is a difference. So, but growing high quality crystal of diamond in HPHT comes at a price. It's a pressure, it's a high temperature. So you need to keep those pressures 5 to 6 gigapascals at 1600 degrees centigrade. And time also. It takes time. So your pressure and temperature have to be at those values for 10 to 15 days. You get very good quality diamond.
So it's not that HPHT is inferior in quality to
No,
CVD.
no.
That's the clarity we
See,
wanted.
the industry grade diamonds are not so pure, right? After all, they're using for abrasive wheels and all that, right? So they use a metal precursor to bring the temperature down. That's all, right? So
Thank you. Thank you.
Yeah.
Thank you, Professor Rao. That was a very insightful session. I'd like to invite Mr. Rajat Wani, who's the Assistant Director of Gujarat Region at GJEPC, to felicitate Professor Rao.
Ah. Good, man. Thank you very much. Good.
Thank you, everyone. We also have our next session beginning shortly, so you all can be seated and attend the same.